Well, it's my pleasure to welcome Bhupal Dev from University of Washington, St. Louis. Um, he is a member of the McDonnell Center for Space Sciences. Um, I He's got a very nice publication list. Um, so how long have you been at the university there? For a few years there? Yeah, so he's been there for 9 years. You just joined Ice Cube as a associate, right? Uh, so what else can I say? Yeah, actually it was an office mate of mine at University of Manchester as a postdoc, and then you were at Heidelberg University. I want you to welcome Bhupal Dev, as he's going to talk to us about a new era in multi-messenger astronomy. So, I'm going to give you that. You can put that on. Might can put that in your pocket or.
Can you hear me? Okay. Okay, so good afternoon. It's my pleasure to be here at Wichita State. It's my first time being here, though I have known Terence for many years, over 10 years, since I was a postdoc at Manchester. He was my office mate for 2 years. So yeah, ever since he has been here, he has been asking me to visit sometime, but I never got a chance, but now I'm here, very happy to be here. Oh, sorry, I'm not sharing to Zoom. Desktop 2, I guess.
Yes.
That should work. Okay, great. Just check 1 second here. Yeah, it moves. Okay, good. So I'm a high energy physicist. I do mostly theory and phenomenology of high energy physics. So you might be wondering what I'm going to talk about in astronomy, right? So what I'll tell you is that this is a very exciting time in this multi-messenger astronomy. And this can tell us, of course, about astrophysical systems, but it can also tell us a lot about fundamental phenomena. And I'll discuss some examples of that. And that's where my expertise kind of comes in. I try to connect the high energy physics phenomena to some astrophysical phenomena. Okay. All right. So let me just start with some very basics, because I was told that there might be some undergrads, master students here. So I'll just give you some basics first. We all know about optical astronomy, right? When you talk about astronomy, we usually think about optical telescopes. Somebody looking at the sky in the visible spectrum. That's up here. In the visible light, and we get light, and then we picture the objects. And in optical astronomy, the size really matters. If you go bigger and bigger in the telescope size, you get more and more collecting power of the light, and then your resolution and your the light collection area, so that all matters to get a better picture of the object you're looking at. And here is the it's kind of the evolution of the optical telescopes over the last 500 years, since the time of Galileo. So Galileo's telescope was really very small. So the aperture was like the size of a dime, and then he made a bigger one with the size of a quarter. But now if you look, it has almost followed like it's an exponential curve, right? As you can see from here, just follows roughly the Moore's law. And now we have telescopes, eventually they become size of the coffee table, then now size of the tennis court. And very soon it's going to be the size of a football field. So that's the 40-meter telescope that's currently being built in Chile. It's called the Extremely Large Telescope. And here you can see the picture of that. So we have come a long way over the last 500 years in optical astronomy. And what we have learned? Well, we got fantastic pictures of different objects, as you'll see in newspapers, in the New York Times headlines, and so on. And especially I want to point out 2 things. One is that it led to profound discoveries very relevant to particle physics. One of them was the expansion of the universe. This goes back to the time of Hubble. That's the Hubble expansion. And the existence of dark matter. Zwicky, later Vera Rubin and all. So they studied these rotation curves of the stars close to the galactic center, and then they pointed out the existence of dark matter. So the improvements in astronomy led to fundamental discoveries in particle physics. Okay? And that will be the theme throughout my talk, actually. So how astronomy helps us learn about particle physics. Now, from optical astronomy, now can move on to what's called the multi-wavelength astronomy. So as you know, the electromagnetic spectrum is very broad, not just the visible light, but you have, if you go down in terms of the frequency, you have the infrared, you have microwave and radio, and if you go up in the frequency, you have the ultraviolet, X-rays, and gamma rays. So you can do astronomy with all of these frequencies. And what do we gain from that? Well, so here is one example. Well, first of all, yeah, it also led to the discovery of cosmic microwave background in the microwave frequency and precision cosmology that we are in today. That's one of the examples of the benefits of going to multi-wavelength astronomy. So here is a picture of the multi-wavelength image of one particular object. It's the Centaurus galaxy. It's not very far away from us. It's about maybe 10 light years, 10, 12 light years from us. Sorry, 10, 12 million light years, not light years. And here you see the images in different spectra, in different wavelengths. So this is the visible light, where you see a bunch of stars. Then at the center, it's obscured by some dust. And that's pretty much it. If you just look in the visible light, you're not going to learn much about this object. But if you look in the X-ray, which is higher frequency or higher energy, then you see this central part of this, which is basically a center. There is a black hole, and there's matter accreting onto the black hole. And so you can see this X-ray picture of the central region. And then if you look in the infrared, then you see the surrounding of the central region where a lot of gas is being heated up. So you get this infrared emission from that, and you see that light over here. And now if you look in the radio, you can see these two blobs. Those are the jets that's coming out from the central region. And so you can see those two lobes very clearly in the radio. Now if you combine all of these different frequencies together, you get this very beautiful picture where it tells you a lot about pretty much the entire thing about this object, right? We have the central engine, a black hole, matter is accreting onto the black hole, then the gas is being heated up, and then you have the jets that are coming out, very high energy jets, and you see all of that together in this picture. So the multi-wavelength astronomy is more than just the sum of the different parts. Okay? So doing astronomy at different frequencies, we learn complementary things about the same object, and we can learn about the object in a more complete way. So just extending this argument further, from multi-wavelength, now we are in this era of multi-messenger astronomy. So far, we have been doing astronomy just with the light, but you can also do astronomy with other objects. Okay? For example, you can do astronomy with particles, with charged particles like the electrons, can do with protons, and we can do with the neutrinos. Okay? So you can do astronomy with those objects as well. And you can also do astronomy with now gravitational waves. Okay? So these are the two important things that have happened over the last about 10, 15 years. You can do now astronomy with gravitational waves and with neutrinos. Okay? So that's what I mean by new era in multi-messenger astronomy. Again, what we learn from that? Well, as just I gave you the example of the multi-wavelength astronomy, you learn more than just the sum of the parts. If you're observing the same object in just the neutrinos or just in the gravitational waves, whatever you learn from that, you learn more than that by combining different messengers. So that's what I truly mean by multi-messenger astrophysics. And here is just a picture showing what are the energy ranges that we cover. With electromagnetic, we cover pretty much the entire spectrum, starting all the way from radio to the gamma rays. But in the cosmic rays, again, we mostly cover starting from GeV all the way up to the highest energies. And in neutrinos, now we are covering, again, pretty much from keV, MeV scale all the way up to the highest energies possible. And then in gravitational waves, we can translate that into some equivalent energy in electromagnetic, and you'll fall in this range. So this has really opened a whole new window into the universe, and it enables new discoveries which are relevant for both astrophysics and also, as I'll tell you, also for particle physics. So let me just give you some brief overview of each of these different messengers, and then I'll go into some examples to show how they have enabled us to know the universe better. So the cosmic rays, they have been known to mankind for about more than 100 years. So Hess was the first guy who discovered these cosmic rays back in the 1910 or 11, I believe. Here's a picture. He's taking his instrument and he's going himself up in the balloon to the sky. That's a pretty scary thing to do. I won't do that. But I'm a theorist maybe. But okay, so yeah, so Hess was the first person to detect these high energy cosmic rays, but now people have discovered cosmic rays over many, many decades in energy, all the way starting from about MeV scale here, going to the highest energy, which is 10 to 20 electron volt or so. So yeah, so you get so mostly in the highest energy the cosmic rays, they're coming from extragalactic sources, and so they interact with the upper part of the atmosphere, and then you produce these showers, the air showers, and then you try to catch these air showers with some array of the detectors. So I believe Wichita State is also part of doing some cosmic ray experiments. So yeah, so you probably will learn more about those from from the researchers here. So although we know about the cosmic rays for about 100 years, the origin of the highest energy cosmic rays is mostly unknown. Okay? We kind of have a rough idea of how they can get to such high energies, but really pinpoint understanding the source of cosmic rays and understanding the acceleration mechanism, that's still an open question. Okay? And so what I'll convey you is that studying the other messengers, and they can actually help us understand the origin of the cosmic ray acceleration. Now, one thing about cosmic rays that is kind of bothering is that you cannot directly pinpoint to the source of cosmic rays just by looking at them on the Earth. And that's mostly because they are charged particles, they're mostly protons, and sometimes the higher energies, they're heavier nuclei, like iron nuclei, for example. And so these are all charged particles, so they get deflected in the magnetic field. Right? When charged particle propagates in the magnetic field, they get deflected. So just by looking at the direction of the cosmic ray, we cannot tell from where they're coming from. Right? And that's true for any charged particle. So that's where the multi-messenger connection comes in, that if we can connect the cosmic ray production with some neutral particle production, like neutrinos, and then because the neutrinos don't get deflected so much, by looking at the direction of the neutrino, we can learn more about the actual sources of the cosmic rays. Okay? So now let's go to gamma rays. So again, gamma rays have been known for, again, more than 100 years. There's a chemist called Paul Villard who first discovered them, and then later people like Primakov, Compton, and also many people studied the astrophysical origin of the gamma rays. So there are three main channels where you can get gamma rays. So in the lower energies, you mostly get it from synchrotron emission, from charged particles going in magnetic fields. They emit light, and that's where you get the gamma rays. And going to higher energies, you mostly get them from some hadronic channels, like you produce pions in the interactions of the protons with either other protons or protons with photons, and then the pions, the pi naughts, will always decay to 2 photons, and that's where you get the gamma rays. And then if you go to even higher than that, then you get gamma rays mostly from inverse Compton, where you have a low energy photon that upscatters against a high energy electron, and that produces higher energy gamma rays. Okay. But here you can see clearly that above 50 TeV or so, there is a sharp drop in the gamma rays, and that's not an accident. That happens because the high energy gamma rays, so the universe is opaque to the very high energy gamma rays. And the reason is the following, that if you have a very high energy gamma ray, then that can scatter against a background light, either the extragalactic background light or just the CMB, cosmic microwave background, and then you produce electron positrons. Okay? So very high energy gamma rays, they will interact with this background photons, and then they will go to lower energies before they reach us. So you do not expect extragalactic gamma rays beyond about 50 TeV or so, and that's the reason why you see this kind of drop here. Okay. So again, bringing in the multi-messenger aspect here, if you see the cosmic rays at very high energies, then you can correlate them with the gamma rays with lower energies, and then you can study about the source in a better way than by just looking at the gamma rays. And again, pointing out this connection with the fundamental physics, the gamma ray astronomy is actually one of the sources which has given us some of the most stringent constraints on the dark matter annihilation and decay. Okay? So if you have some dark matter particle that's decaying to photons or annihilating to photons in the final state, then you can look for them, for example, from the galactic center or from from the diffuse sources and so on. And these are, so gamma ray astronomy gives us some of the best limits on the annihilation cross section or the decay lifetime of the dark matter. So this is, again, this is very important for doing fundamental physics. So now coming to the neutrinos, that's another messenger that we discussed earlier. So again, so neutrinos come from various sources, and as you can see from this plot, they span over more than 20 orders of magnitude in energy, starting from this cosmic neutrino background, which is just like the cosmic microwave background for photons. This is a relic coming from Big Bang. We know this exists, but so far nobody has detected it directly. There is some indirect evidence for this. All the way, then go to solar neutrinos, the supernova neutrino reactor, and then then some diffuse supernova background. There's accelerator neutrino, which is not shown here. Many people here work in accelerator neutrinos. And then there's atmospheric neutrinos, then the astrophysical, and then cosmogenic neutrinos. So you can see that as you go to higher and higher energies, the flux is going down rapidly. So if you want to detect these neutrinos from these kind of sources, you need a very big detector just to compensate for the decreasing flux. And so the history of neutrinos having multi-messenger signals, that goes back to many years, about 50 years or so. The first multi-messenger signal in neutrinos and photons was the discovery of the solar neutrinos. As you're probably all familiar, so in the 1960s, there is this puzzle called the solar neutrino problem. So the theoretical calculation of the solar neutrino flux was consistently about a factor of 3 higher than the experimental measurement of the fluxes. And this happened across many different experiments, so it cannot be just a systematic. And then later, this was one of the key motivations for studying the neutrino oscillations, and this played a key role in the discovery of the neutrino oscillations, which got the Nobel Prize finally. Another very important multi-messenger signal that was discovered relating to neutrinos was this supernova 1987A. There are 3 experiments, IMB, Kamiokande, and Buxton, where they observed neutrinos from this particular source, 1987A, which is in the Large Magellanic Cloud, about 50 kiloparsecs away. And then they went back to the optical data, and then from there they could really see before the burst and after the burst for the supernova signal. So this was truly a multi-messenger signal. And this has again helped us improve the supernova modeling, our understanding of how stars die. At the same time, they have helped us get better constraints on many light particle phenomena. Like if you have some light dark sector particles like axions, dark photons, G prime, whatnot, you can emit these particles from supernova, and then they will take away energy from the supernova core. And by comparing with the neutrino luminosity, you can actually put a bound on the light particle coupling to the standard model particles. Okay? So this has opened up a whole new field in this light dark sector physics. All right. And now, over the last 10-15 years, there is a new branch of neutrino astrophysics. This is the high energy neutrino astrophysics, where we look for the neutrinos at higher energies. By high, I mean beyond TeV scale, TeV, 100 TeV, PeV scale, that range of energies. There are 2 main processes which contribute to this high energy neutrino flux. So if you have some objects like you have a cosmic ray reservoir, like a starburst galaxy or galaxy cluster where new stars are being formed, there's high density of matter there. And these are some of the cosmic ray accelerator sources or cosmic ray reservoir sources. So if you have very high energy cosmic ray hitting some ambient proton, and from there you produce pions, and then the pions will decay, the charged pions will decay to muon and a neutrino, and then the muon will further decay to electron and neutrinos. So for each of these pion decay, you get 2 muon neutrino versus 1 electron neutrino. So 1:2:0 in the flavor ratio. And that's the source of these high energy neutrinos. So at the same time, you produce also neutral pions, and the neutral pions will always go to 2 photons. So there is a connection here you can see between the neutrino flux and the photon flux. Okay? That's the multi-messenger connection here. And that's also related to the original proton flux, which is the cosmic ray flux. There's another way you can produce the high energy neutrinos, that's through the p gamma interactions, and this happens in places where you have cosmic ray acceleration mechanism, like in a active galactic nucleus or in a gamma ray burst or blazars. So in this case, you have a proton photon interaction, and then again the end product is always pions, and then pions will go to muons and neutrinos, and then muons will go to electrons and neutrinos. So in both these cases, you do produce neutrinos as the end product from the pion decay. And these neutrinos are then can be looked for. So this is a if you study these neutrinos, they give a direct link to the cosmic ray acceleration mechanism. As I was mentioning earlier, the neutrinos are neutral particles, so they straight come to us. So if you can pinpoint the direction of the neutrino, then you do know where the cosmic rays also are coming from. And this picture kind of illustrates this idea a little bit in a better way. So on the x-axis is the energy, and the y-axis is the flux times the energy square. Because usually you expect the flux to go as a power law, typically e power -2 for the neutrinos, and that's why if you have E square times phi, that should be a constant. Okay, in this, so that's kind of the standard expectation. So we have the data from the high energy cosmic rays, let's say from AUGE or from telescope array, and then we also have the gamma ray the gamma ray spectrum from Fermi and from other observations. But the missing piece was in between, which was the neutrino, and this is what was seen by IceCube in the last 10 to 15 years. Okay? So it fits very nicely in between these two. So from the protons, you get roughly 1/20th of the energy of the proton will be converted to the energy of the neutrino, and then from the pions, and this is from the charged pions, you also get for neutral pions, you'll get photons, but those photons will scatter down to much lower energies, and that's what you'll eventually see in the lower energy bins. Okay, so you go from here to here to here. So it's a very nice transition you can see from here. Okay, and this is supported by the data. All right. Now the final frontier, which I'll discuss about, is the gravitational frontier. So out of these 4 multi-messenger, we have the cosmic ray, we have the gamma rays, the neutrinos, and then the gravitational waves. So this is something that, again, this has been made possible by the discovery of the gravitational waves and by in the LIGO experiment in 2015. So you can get gravitational waves from many different sources. So the ones that LIGO detected was over here, about a frequency of a few hertz. So that is coming from the merging of two black holes, 2 compact objects, either 2 black holes or 2 neutron stars, or 1 black hole, 1 neutron star, right? But you can also get gravitational waves from many other different sources. For example, you can get from what is called EMRI, the extreme mass ratio in spirals. Like you have a supermassive black hole and a small black hole. From there, you can also get gravitational waves, or you can get gravitational waves from the merger of 2 supermassive black holes. But their frequencies are going down over here. As you can see, the wavelength is increasing. So these ones cannot be seen by the ground-based observatories. You have to do either go to space-based interferometers, or you have to do some kind of other techniques like this pulsar timing array, where you use the whole Earth as kind of the detector, and you put the timing arrays across different parts of the Earth, and then try to measure this over many years. And if you go to even smaller frequencies like this, below the nanohertz frequencies, then you can also get gravitational waves from even from the inflation, from very early phases of the universe. Okay, so you can use the gravitational waves not just to study these compact object mergers or mergers of supermassive black holes, but you can also do early universe cosmology, like you can study phase transitions where you can produce also gravitational waves, or you can do topological defects or inflations and reheating and so on. So this also has a lot of importance for fundamental physics phenomena. All right. So that's basically these 2 observations, the high energy neutrinos and the gravitational waves, that led to this new field of multi-messenger astronomy. And as I said, this is a new opportunity for new physics searches in addition to studying astrophysical phenomena. So I'll give you 2 examples of that. What kind of new physics we can search for using this. And the first one I'll look at is this multi-messenger neutrino astronomy. So first of all, let me just briefly discuss how these high energy neutrinos are being detected. The screen is a bit dark, maybe you can't see this very clearly, but so this is the IceCube detector at the South Pole, and this concept is kind of very nice. So you just dig holes in the ice, and you put photomultiplier tubes down like a few kilometers in the ice. And so if a neutrino comes by, it hits the ice in the detector or outside the detector, and then it produces a charged particle. Then this charged particle travels at a speed faster than the speed of light inside the medium. It gives a Cherenkov light, and you just collect this Cherenkov light using the photomultiplier tube. Right? So that sounds very simple, but of course you'll always have to deal with backgrounds. Most of the backgrounds are cosmic ray backgrounds. So there are 2 ways that deal with this cosmic ray background. One is that if the event is coming straight down to you, then they put another array here called the I-stop. So you veto those events which hit both I-stop and the detector. So that will be a cosmic ray event. So they veto that, and then they only look for the events which are originating inside the detector. That's called the content event, or the starting events in the detector. You can do also another thing. You can shield this the events from cosmic rays by just using the Earth as the shield, because at such high energies, the Earth also becomes opaque to these high energy events. So if you are having upgoing events, like as shown in this picture here, then these events are coming through a lot of Earth matter. So it is shielded by cosmic rays. There is a lot of overburden here. So only neutrinos can penetrate, but the charged particles cannot do that. So then the neutrinos, they produce a charged particle, here in this case mostly muon, and then the muon just goes through the detector, gives a track. Okay? So that's how they know that this is a high energy neutrino event and not a cosmic ray event. Now this particular sample is called the through-going sample, because the muon is through-going. It has so much energy that it just goes through the whole detector without being stopped. So it loses energy, of course, but it just goes through the whole detector. Now these events are very good, especially because they leave a very nice track. So you can pinpoint that track, you can reconstruct that event back to the sky, and you can try to look for the point source which gave you this signal. Okay? And that's so that's the origin of this multi-messenger signal, essentially. And IceCube did that recently, well, in like maybe a few years ago. So first they had a hint in 2018 from a blazar. This is called the Texas source, the TXS0506 source. And they had about 3 sigma evidence that from the direction where the neutrino is coming from, and you can connect that to some gamma ray activity, and they found a blazar in that area, and they could get 3 sigma correlation between the blazar, the blazar signal and the neutrino signal. And more recently, they did this with 2 other sources. One is this NGC 1068, and another is PKS 1424. And so here you can see the actual data from the IceCube paper, the 2022 paper. And they detected about 80 neutrino events from this single source. And then they do a correlation. There's a spatial correlation in the sky. This is the right ascension and the declination. So this white point here is the best fit for the direction of the neutrino, and there's a 1 sigma and 2 sigma. And then in the red, you see this is the best fit point and the 1 sigma from the optical, okay, in that same region. Now this NGC 1068, this is a very bright active galactic nuclei. Actually, it's the second brightest galactic source, extragalactic source in the sky. It's at about 15 megaparsec from us. So they know its properties very well, and now you can correlate with a very high confidence. You can correlate the neutrino signal to this to the photon signal, and from that you can tell that yes, the neutrinos are indeed coming from this particular point source. And what is crucial for this discovery was this angular resolution made possible by these through-going tracks. So what you see here is the angular distribution the events as a function of angular distribution. So if you are above few degrees, if your resolution is worse than a few degrees, then you see that events are consistent with the background. Okay? But as soon as you put a cut here below 1 degree, you suddenly see an excess of the events over the background. Okay? So that was the key point that helped them find this particular point source. And now the evidence is, I think it's more than 5 sigma. Yeah, here it shows 5.2 sigma local significance. Okay, so what can you do with this source? Okay, you know that the source, but there is a source which emits the photons and it emits the neutrinos. Now, so what? Okay, well, first of all, this particular source, as you know that the neutrinos are coming at such high energies. Okay, I don't have the energy distribution over here. I'll show it later. But these energies are roughly 100 TeV or so. Okay, very high energy neutrinos. And if you know that a source is capable of accelerating the neutrinos to such high energy, then there must be some progenitor for that, which is accelerating these neutrinos. And that cannot be anything but the cosmic rays. So this source must be also producing cosmic rays at high energy. Okay? So this at least solves part of this cosmic ray origin problem, that we know these kind of sources with active galactic nuclei, they do accelerate cosmic rays to such high energy. So that's one evidence we have. And there is something more, which I'll tell you about later. But before that, we can also use this to do even answer some more fundamental questions, like what is the origin of the neutrino mass? This is another fundamental puzzle over the last many years. We do know neutrinos have a small mass, but we do not know where their mass is coming from or what is the nature of that mass. In particular, neutrinos are the only neutral fermions in the Standard Model, neutral fundamental fermions in the Standard Model. So they can have two types of mass. So they can be Dirac particles where the neutrinos are different from the antineutrinos. That's called a Dirac particle. Like the electrons, they are different from the positrons, or protons, or the quarks are different from antiquarks because of the charge. But for neutrinos, they don't have electric charge, but still they could be different from the antiparticle. And they also, because they're neutral, they can also be their own antiparticle, and that's the Majorana neutrino. So this is a fundamental question whether neutrinos are Dirac or Majorana. Okay? We don't know the answer. The best way to look for this question, look for the answer to this question, is by doing an experiment called neutrinoless double beta decay. So you all know about beta decay, single beta decay, where a neutron goes to proton plus electron plus anti-electron neutrino. Now you have certain nuclei, about 10 nuclei that exist, which can do what is called a double beta decay. Now a single nucleus, you can emit two electrons and two neutrinos, two electron antineutrinos. So here in this kind of nuclei, the single beta decay is actually kinematically forbidden, and the double beta decay is kinematically preferred, so you can do that. And this has been observed, by the way, and the half-life is very large. It's about 10⁻21 years, but this has been observed. Now, if the neutrinos are their own antiparticles, then you can do what is called a neutrinoless double beta decay. You can just connect these two neutrino lines here, and then you emit only two electrons but no neutrinos. Okay? That's the neutrinoless version of this double beta decay. This process has not been observed. And in fact, there is a theorem called the black box theorem that if this process is ever observed in nature, then neutrino must be Majorana particle. Okay? And this you can prove very rigorously, that only if neutrinos are Majorana particles you can do this process. So people have been looking for this for many years. There have been lot of experiments going on in the world, and there are also some planned experiments like ton scale experiments looking for this double beta decay signal. And the current status looks something like this. So you have the lightest neutrino mass on the x-axis here, and this effective Majorana neutrino mass on the y-axis. And these are the current bounds in gray here. The best bound currently comes from this Kamlan-Jen experiment looking at the decay of the xenon 136 nucleus. And the bound they obtain is roughly less than 0.1 electron volt roughly. And in the future, they plan to go down to about another order of magnitude in this next experiment, which was sadly cancelled, by the way, recently. But there is another version of this called Legend, which is in germanium, and that has been approved, so they can also go down to roughly that same level. So this is the theoretical prediction you would expect if neutrinos are from the Standard Model. Well, when I call Standard Model plus the neutrino mass. And if they're in inverted order, then you'd expect them to lie in this range. And then if they're normal order, then you would expect this effective mass to lie in this range. Now, as you can see here, what is unfortunate is that if they're normal order, and that's something that is currently what the global field prefers, that neutrino mass should be normal order, then you may be living in this kind of funnel region here, where there is some accidental cancellation happening between different phases. If the neutrinos are Majorana particles, there are two more phases along with the standard Dirac phase. They're called the Majorana phases. And there is some accidental cancellation happening here. Then you are in this funnel region where even if the neutrinos are Majorana particles, still you may not get any signal in the double beta decay experiment. Okay? This could happen. If nature is cruel to us, this could happen. So in that case, what do we do? How do we then proceed further? Okay? So there are few other alternatives, but none as good as this. There is no theorem as such, but there are some alternatives. One of the alternatives is going to colliders, high energy colliders, where you do not look for directly the neutrino, because neutrino is just a missing particle in colliders, so you can't really study them directly, but you look for the associated particles which keep mass to the neutrino, okay? Like the messengers of the neutrinos, like right-handed neutrino, for example, or some heavy gauge bosons or whatever, and look for the signals of those. And if neutrinos are Majorana particles, then you will have left a number of ovulations somewhere in your theory, and then look for those in the high energy colliders. So this is of course a great alternative, and people have been doing this search, but so far there is no signal. Okay? So I'm going to propose another alternative here, which can be probed using astronomy. Okay? Okay, so this is a possibility called the quasi-Dirac neutrinos. So again, so just to give you the basics here, we do know in the standard model the neutrinos are what is called the left-handed. That just means that the spin and the momentum they are aligned against each other. Okay, that's what we mean by left-handed neutrino. And in the standard model, there is no right-handed neutrino, okay, where the spin and momentum are aligned with each other. The simplest way to give mass to the neutrino is just add this right-handed component by hand. Okay. And if you do that, then you simply can write what is called the Dirac mass term here, which is just the psi L bar psi r, the left-handed neutrino and right-handed neutrino. You can write a Dirac mass term. And then you can also write what is called a Majorana mass term, because that is not prevented by gauge symmetry. Okay, that's allowed by the gauge symmetry. So if you do that, then there are two possibilities, right? If this term is exactly 0, let's say by some symmetry arguments, then lepton number is exactly preserved, and neutrinos are Dirac particles. And this you can see immediately from this 2 by 2 matrix, that if you set this term to 0, then so one of the eigenvalues must be 0. So that means if this term is 0, then the eigenvalues are just plus minus md. So they form a Dirac pair. So one mass is plus md, one mass is minus md. Now, if this term is not 0, then neutrinos must be Majorana particles, because there is lepton number violation. But there is a limit you can go where this term is much smaller compared to the off diagonals. Now, if this diagonal is very small compared to off diagonals, then you are kind of going to the Dirac limit. But if this is not 0, then you still have a small lepton number violation in the theory. So the theory somehow knows that you have a small lepton number violation, right? And this is the scenario that I call the quasi-Dirac. Right? This neutrinos fundamentally Majorana particles, but because of this small mass difference, they behave like Dirac particles in everyday setting. In all lab experiments, you will see them as Dirac particles. Okay, so there's very small active sterile mass splitting. Now, those of you who are experts, you might wonder, okay, why this is a good possibility. The more natural possibility is to have this term much larger compared to the Dirac mass. Okay, this is called the famous seesaw mechanism, where the neutrino mass is explained, the small neutrino mass is explained by the large mass for the Majorana particle. Okay, so that's called the seesaw. But of course, this is a very good possibility, and this is motivated from some grand unification and so on. But the other possibility is also a logical possibility. I mean, mathematically, this is still possible. This is allowed. Okay? So if it's mathematically allowed, then we should definitely study it, and then it's up to the experiments to find out which one is the right one. Okay, without having some theoretical prejudice here. And there is another strong motivation which I did not know about until very recently, that this possibility is actually motivated from string theory. Okay, it's a very unlikely place, but yes. So the Dirac neutrino is actually preferred by what is called a swampland conjecture in string theory. Now, I am not a string theorist, but the basic idea here is this is mainly the work of Oguri, Bhafa and company. The idea is that if you compactify the standard model on a circle, then you get what is called some unwanted vacua. You get many vacua in the string theory, right? And only one of the vacua is the right one, which is our standard model. And there are some other which are like standard model, but many of them are unwanted vacua. They have very bad properties. You don't want to live there. That's why it's called swampland. So if the neutrinos are Majorana particles, then actually you will get more such unwanted vacua than if they're Dirac particles. And if they're Dirac particles, you can actually cancel the bosonic degrees of freedom from photons and gravitons against the neutrinos, and then you can exactly live in the standard model that we have very happily. So this is this is a conjecture, of course, but in this case the neutrinos must be Dirac. Now, we do know also that Dirac means that there is a global lepton number symmetry, and any global symmetry must be broken by quantum gravity at high scales, because quantum gravity doesn't like any global symmetry. Black holes eat all the global symmetries. So that means that you start off with a Dirac neutrino at a high scale, and then it's broken by some high dimensional operators, and that would predict you some sort of Dirac nature or the quasi-Dirac feature. So it's a very natural prediction of the swampland conjecture, actually. Okay. So that's the theory part. So how do you probe it in experiment, and what has it to do with astronomy? Okay. So to probe this very small mass difference, you need to have very long baseline. Okay. In neutrino physics, in neutrino oscillation physics, the quantity that matters is this combination, is delta m square, mass square difference, L over E, and the sine square of that. That's the probability. So the probability of the oscillation is proportional to this quantity. As delta m square is the mass square difference, L is the oscillation length, and E is the energy. So if you have very small mass splitting, delta m square is very small, then you need very large length, oscillation length, in order to get some significant oscillation effect, right? So you need to go to astrophysical baselines to show this kind of effect. And this is what is shown in this picture here. The x-axis is the oscillation length or the baseline length, and the y-axis is the energy. And you see different combinations here of delta m square where this quantity is order 1. Okay? So just for reference, here I have shown the atmospheric and the solar mass square differences, but this is for active-active. But here what I'm showing here is active-sterile. So this is just for reference. So you see that if you are at very small mass square difference, like 10 to the minus 11 eV square, that's exactly where the baseline of the Earth sun distance is, one astronomical unit, 1 AU, 10 to the 11 meters, right? So looking at the solar neutrinos, we can actually rule out any mass square splittings larger than 10 to the minus 11 eV square for active sterile. And this is a current bound we have. But beyond that, we do not have any bound at the moment. So what are the other sources of astrophysical neutrinos that we have? Well, we have the supernova neutrino, the 1987A, but only got handful of events, like 20-25 events from that. Still, using that, we can also study this active sterile mass splitting, and this is what was done in this paper. And they found that you can actually probe delta m square down to 10 to the minus 19 eV square. See, the very, very small mass splitting between active and sterile. But again, because the statistics were so low, you only are sensitive to very narrow range of delta m square, because the oscillation length is fixed here with the 50 kiloparsec, the distance to the supernova, and also the statistics was low, so the confidence level is also very low for this constraint. The other thing you could do is, if you look all over the sky, then you have this diffuse supernova neutrino background. This is the neutrinos coming from all over the sky from various supernovae happening all over the universe, right? Now this has not been seen so far, but there is a prediction that there is such a flux exists, and if this is seen in the future, then this can help us to go down to even smaller delta m squares, like up to even 10 to the minus 25 eV square. It's a very, very small mass splittings. And at some point you have to stop because you hit the observable universe, like the length becomes the size of the observable universe. Then you can't do anything beyond that, right? That's roughly 10 to 27 or 28 meters, I think. But there's another thing that you can do if you go higher up in the energy, and that's what is shown here. This is the high energy neutrino I was talking about earlier that IceCube has seen. So using those, you can also see that for those energies about TeV scale or 100 TeV scale, you are also sensitive to 10 to the minus 13 to minus 20 minus 18 electron volt square. So there's a wide range of masses, mass splittings that you're sensitive to if you look for the high energy neutrinos. And that's exactly what we are doing here. This thing died. Okay, so that's what is the new probe of the quasi-Dirac neutrinos, and this is enabled by this multi-messenger astronomy. The idea is very simple. You look at a source, if you know that your point source of neutrino is located at some distance, and that's the NGC 1068 I gave you the example of, right? So you know the oscillation length here, that's fixed by the redshift of the source, and then you know the energy, you measure that in the detector, and then only thing you don't know about this delta m square. So you try to match these quantities and look for the delta m square, what will give you the maximum probability here of the oscillation of this active to sterile. And what would happen is that if the neutrino is produced as an active and then it reaches you as a sterile, then you lose half of the flux because the sterile does not interact with the matter. That's why it's called sterile, right? So you lose half of the flux, and then if you know the original flux, then you can tell what will be the final flux after oscillations. And if you don't see that, then that's a constraint on this particular model. Okay, and just to show mathematically, I think the battery is down. Yeah, so this is the actual oscillation probability just by using this formula. It's a little bit more complicated than that, but yeah, you get something like this. This is the disappearance probability, nu mu to nu alpha, nu sterile here, sorry. And for particular energies, for particular delta m square, you can see that this oscillation probability can be maximal, can be order 1. That means that if you are sitting in one of those resonances here, not resonance, you are sitting at one of these peaks here, then you get maximum disappearance of the mu neutrinos from the sources. And using that, you can actually put a bound, and this is something that you would predict if we had such active sterile mass splittings, then you would expect this kind of event spectrum shown by the colored band here. And what the data has is this, right? So you can see that this is energy dependent deficit in each energy bin, right? Now you can imagine that, okay, you can tell me that no, I don't know what is the original flux, so how do you know that this is just a deficit, but not, but if it's not some overall reduction in the flux? But so that's where having multiple sources helps us, because if you have a particular mass square splitting, then you can probe them across different del times different E and different L, and the multiple sources provide you a different L, and they also give you a range of the energy. So you combine all of this together, then you can remove this astrophysical uncertainty that this is some overall caused by some overall flux normalization. And using that, one can actually derive a constraint on the del time square. And now you can see that now we are covering a wide range of the del time squares. Okay? So just for comparison, the supernova constraint that we had is right here. It's just in a very tiny window. But now with IceCube, this is actually with IceCube data, you get a constraint which is much broader across many different orders of magnitude in the del time square. And in fact, recently in the latest IceCube data, there seemed to be some hint of this active sterile oscillations. So we got very excited about it actually, and this was in a recent paper with the Harvard IceCube group, Carlos Arguelles and his student Chiara Carloni. So the IceCube had two different samples. One was the cascade sample. This is basically all the electromagnetic showers they had in the detector, and one is called the Estes sample. That's the okay, I forgot what's the exact form of this, but this is basically the starting energy sample with a track attached to it. So this is a muon track, but it starts inside the detector. It's not just through going muon, but the muon starts inside the detector. So if you look at the spectra for both of these, you see that they don't match with each other. So the Estes sample, they have this is the orange color data points, and they have a different powerless spectrum than the cascade data sample. So you can't explain both the samples using a single powerless spectrum. But if you use the quasi-Dirac hypothesis oscillations, then it seems like you can explain both of them nicely. Okay, and using that, you can actually derive a test statistics, and this is the result that we got. That if you just you get a preference. This negative delta TS means is a preference for a non-zero del time square, and you get this at the level of about 2.8 sigma or something at 10 to the minus 19 electron volt square. And also you get a ruled out region, which is this more than 3 sigma ruled out, just above that. So we got really excited about it, that okay, this is the evidence of a sort of Dirac neutrino, quasi-Dirac neutrino. But our happiness was short-lived because there are a lot of uncertainties here. Okay, we are playing with a lot of astrophysical uncertainty, and most of the uncertainty is coming from the source distribution. Because we are doing a diffuse flux analysis, that means that we are looking at all sky coverage, and we have to know. So we are using point source here, but you have to know like how are the point sources distributed in the sky. Because before what we did was just for one point source, the NGC 1068. We know where it is. But now if you're trying to do a diffuse analysis, because that's this analysis, the data is for diffuse analysis, then you have to know the source distribution. And this is something that we really don't know. So we can make a best guess by looking at the star formation rate of the, because that will track the, the roughly the AGN distribution, and from there you can make a guess. But that's really a guess, because you can have different types of distributions. There are different redshift dependence. So once you include all of that dependence, then the significance goes down quite a lot. And now we can still have the exclusion region. This seems to be robust, but the preference that we had earlier, that seems to be gone now. Okay. So of course we need more statistics here, and this is just the first 6 years of data in Cascade and first 10 years of data in Estes. But in the future, IceCube is going to run for many more years, so they are going to improve the statistics, and hopefully we'll get better better data where we can tell something more about this. But this is something that's really interesting, that you can use this as the multi-messenger data for the for the high energy neutrinos, and you can study the fundamental property of neutrino, like whether Dirac or Majorana particles. So that's kind of cool. Okay, so We have 5 more minutes. Is that right? Okay, good. So another thing that he can do, he can study the properties of dark matter. That is another fundamental problem. We do know dark matter exists and it has gravitational interactions, but we do not know what are the other interactions of dark matter with nature, right? Now, using again this this multi-messenger connection, that we have the high energy neutrinos, that means we have high energy cosmic rays being accelerated very close to the center of the black hole. We can also study the properties of dark matter. Again, the idea is very simple here. So there is a recent paper where they calculated what should be the maximum distance within which the cosmic ray must be accelerated to produce these high energy neutrinos that we see. Okay, and they came up with this number roughly about 10 parsec from the central supermassive black hole. Okay. Now 10 parsec is a very small, okay, to us it looks like a large number in the context of the Earth, but actually in the cosmic scales this is a tiny number, okay, because the source is located at some gigaparsec away. So this is 1 part in 10⁹. Okay, the source has to, the acceleration mechanism has to happen within this very small distance, you know, compared to the central engine. And if that is true, then you can bring in the dark matter connection here by noticing that every galaxy, it hosts a dark matter halo, right? And that's kind of accepted that galaxies host dark matter halo like our Milky Way, and the closer you go to the center, the dark matter density increases, right? And that's expected because if you have a black hole at the center, then you have a huge gravitational potential, so you would expect more and more dark matter to be accumulated closer to the black hole. Of course, all the way up to the event horizon. Below that you can't have anything, but up to that point you have a large dark matter density distribution, and that leads to the concept called dark matter spike. Okay, this was an idea proposed by Gondolo and Silk back in 1999, that if you go closer to the center of the galaxy, you should expect a large increase in the density of the dark matter, okay, which is shown in this plot here. This is the distance from the center of the galaxy, or the distance from the supermassive black hole at the center, and this is the density. And if you have the standard, the NFW profile of dark matter, you expect this to go like that, which also itself is a Cosby profile. It goes as 1 over r. So if you go to r equal to 0, this blows up. But because you have the central supermassive black hole, which is a huge gravitational potential, at some point you would expect to have a spike profile which even goes even further up, many orders of magnitude higher density than what NFW predicts. So now there are many different mechanisms where, like, does it keep on growing or does it stop somewhere? There is something called the stellar heating. There is some also you can have annihilation of the dark matter, which will kind of make it plateau and so on. But the point is that you get large enhancement in the flux of dark matter or the density of the dark matter close to the black hole. Now, if you're accelerating the cosmic rays in this region and you have a large density of dark matter, then you can imagine that if your dark matter is interacting with the protons, then that will act like a frictional term, right? Because you have a fluid of dark matter, and then you're moving this cosmic ray particle through that fluid, and then if you have a large interaction, then this will cause like a drag to the cosmic ray, right? It's just like a viscous drag. You're trying to move a particle through a fluid. If the fluid has high viscosity, then the particle is going to move, is going to slow down. And what could happen here in this case, because the energy is so high, you are talking about TeV or PeV energies here, right? A PeV energy particle, it's hitting a dark matter which is sitting at rest mostly. It's going to completely break apart the cosmic ray particle. Okay? So if it's a deep inelastic scattering, right? So if it's a proton, it's going to just break apart into quarks. It's going to lose energy very rapidly. Or if it's heavier nuclei like iron, it's going to be shattered completely. It's going to be fragmented into lower nuclei. And this actually gives a very strong bound on the dark matter proton interaction strength. And that is shown in this plot here. This is some work that's still in progress with Matthias Hostert, who just joined as a faculty at Iowa, and Mike Berger, he's a postdoc in Melbourne. So what we find here is that as a function of the mass of the dark matter, you can put a constraint just based on the fact that we observe such high energy cosmic rays and they are not broken apart, they don't lose energy, otherwise you would not have observed them at that energy. Just using that argument, we can put a bound on the dark matter proton cross section, which is at this level. And just to compare, this is the current limit coming from the direct detection experiment. So CREST, there is also recent limit coming from the LZ, which is here. We can get a much stronger bound compared to that just by using this this multi-messenger source physics here. And this can probe some interesting region of dark matter parameter space where you can get the right relic density using what is called the Frisian mechanism. All right. So I don't have maybe much time, but there is this another multi-messenger frontier which I did not discuss, which is the gravitational wave frontier. So there is this particular event called the GW170817. This was the merger of two neutron stars, and this was followed up by many different searches. So first it was seen in gravitational waves, of course, by LIGO, Virgo. And then it was seen in photons in the gamma rays by Fermi-LAT, by Fermi GBM, Fermi Gamma Ray Burst Monitor. Then it was also seen by X-rays and UV in optical IR radio. So many telescopes followed it up, and they all saw signals for this event. So this is a very well studied event by now, and this has really opened up a whole new area of of astrophysics. The multi-messenger astrophysics using gravitational waves. You can look for, you can study the relativistic astrophysics. You can look for extreme nuclear matter physics, nuclear synthesis, and so on. Many things you can do. Along with that, you can also look for some exotic particles in this case. Okay, and this is one thing that I would like to mention before I stop. So you can do what is called the axion search, or I'm just taking an example of axion, but you can do actually any light particle that couples to the nucleus. Okay, the basic idea is very simple again here. You have this neutron star merger, and then you can emit such particles if they couple somehow. Let's say they couple to photons, then you can produce them because you have photons coming out from this object, and you can couple these particles to photons, and you can also emit these particles. Now you can do three different kinds of searches here. One is called the thermal search, where you just look for the effect of this particle on the properties of the neutron star itself, right? Because neutron star, when they collide, then they make one bigger neutron star, or they collapse into a black hole. You can look for the effect of the evolution or the effect on the gravitational wave spectrum itself if you have such kinds of objects. And people have looked for this object, and it turned out that those are very negligible. Even if you make a very large coupling over here, then still the thermal effect is very small. The second thing that you can do is that you look for the production of a particle, let's say the axion. Then axion converts into a photon in a galactic magnetic field. Okay. And then you look for some extra photon signal over here. But this you can only do for very small masses because the galactic magnetic field is very small. It's nano Gauss something. The third thing that you can do here is the decay of axions into photons. Okay? So you produce these axions here, and then they decay to two photons, then look for that photon signal using Fermi. Okay? And this is something that leads to a bound on the axion because we have not seen an extra photon signal. So you look for the gravitational wave. It arrives at some particular point of time called t equal to 0, and then you look for a photon signal within t equal to 1 second. Now why 1 second? Because beyond that you are also going to get photons from the merger itself, and this particular delay is happening because the photons take time to get out of the messy object here of the debris of the axion of the neutron star merger, but that takes some time. So before that, if you get a photon signal, then that must be from new physics, because you can't otherwise get out of that messy environment. So you look for that, you do this timing study, and then you can actually derive a bound in the mass versus coupling plane of this axion. So this plot is very busy, but the point is that you get a bound which unfortunately is already ruled out by other things. The bound is not strong enough, but this is just one event, right? You can imagine that just with one event you can get a bound, but now with multiple events you can do much better. So there is this debate of which one is better in getting the axion bounds better, whether it's a supernova or a neutron star merger, and the answer is that it could be both. It could be either. Sorry. So there are some advantages of having a merger, but there is also some advantages of having a supernova. We don't know which one will occur next in our galaxy. If a supernova goes off in a galaxy, then of course that's the best thing that you can have. But if that doesn't happen, because the rate is very small, it's like 1 over half a century. On the other hand, for a merger, you can look for very distant mergers because you're looking in gravitational waves. They can probe to up to gigaparsec distance. So if you do that, then you get like roughly 10 to 1,000 mergers per year. So that could really improve this bound to something like this in the future. And also there is this the timing information that you can get in both cases. There is this early warning system that's in place, which is called the AMON, the Astrophysical Multi-Messenger Observatory Network. And for supernova itself, there is this thing called snooze. So you can do the timing very precisely. So if you look for a gravitational wave signal, then you also look for a photon signal within 1 second. If you get such a signal, then that would be a clear-cut signal for some new physics like these axions. Okay, so with that, let me just conclude. So this is an exciting era of multi-messenger astrophysics. We have gotten events from the same source in different different spectra, with using cosmic rays, using photons, using neutrinos, and hopefully also in the future you'll get some event which Francis Halgin said event of lifetime, that you get a simultaneous observation of electromagnetic, cosmic ray, neutrino, and gravitational wave. So that will be really, really fascinating. Okay, and this multi-messenger astronomy has opened really new window into the universe. In most cases, opaque universe where you cannot access them by photons, but you can access them by neutrinos now and also by gravitational waves. So they have new opportunities for doing fundamental physics, and they are complementary to the other probes of the new physics that we have in the on the Earth. Okay, thank you so much.
For the ice cube measurement or analysis that you showed for the sterile bounds, what are the prospects as they collect more data? Will that open up additional sort that you'll do?
Right. Yeah. So here this is the current bound from whatever 10 years of data that IceCube has. Well, for this particular 3 different sources, if you just combine them together, then you get a exclusion region which is at the level of 2 sigma at the moment. And what is shown below here is the projected bound from IceCube Gen 2, which will be like 8 times more volume, and also they will have more sources. So here I have listed 9 different sources. So these 3 sources plus 6 other sources, and these are not like random sources, but these are the sources. Already IceCube has like 1 sigma confidence that these are multi-messenger sources, but now with more exposure they can probably go more than 3 sigma there. And if you combine all of this together, then you can see that now you can push this exclusion to about more than 5 sigma. So, and that means that if it is there, signal is there, then you would definitely see that. This is yeah, this is probably another maybe 10-15 years. That is Gen 2. It's not approved yet, right? But right, but we do have other experiments coming up, like KM3net is currently under construction. That's not a 10-kilometer cube, but that's another adding 1 kilometer cube. And then there's a P1 in the Pacific Ocean. And then China is building this thing called Trident in the South China Sea. That's going to be like they say 30-kilometer cube. I mean, right now the first phase is approved, which is I don't know 1 kilometer cube, but they plan to make it to 30-kilometer cube. So if all of these things happen over the I don't know next 10-20 years, then we could get a significantly larger sensitivity to this. Yeah, even if IceCube Gen 2 is not built. But what I hear from IceCube community, they are saying that IceCube Gen 2 will happen at some stage. I don't know when. No, not yet. No, because none of the other experiments like KM3net and all, they have not identified any particular source yet. It's only IceCube which has identified the sources. Yeah. So KM3net is under construction and they have some events, but they have not pinpointed the source yet for those events. Yes. So yeah, so this is exclusion I'm showing. So yeah, 2 sigma exclusion is probably is not much, of course. Yeah. But in the future, so I mean, what I'm showing is that this has some potential to answer one of these fundamental questions, the nature of the neutrino mass, right?
They need to take the ocean deeper.
So yeah, in the South China Sea, they have identified a region. I don't know, maybe that's the region they want to invade Taiwan, because that's closer to Taiwan. There's a place in Taiwan where it's very close to Taiwan, that they have identified this particular place, which has a kind of a very quiet region. There's no mountains underground under the sea and so on. So they have a flat region there, and they want to do this 30 kilometers. It's called Trident, I believe, and there's a first phase of that is called Hunt. So I think Hunt has been approved, but that's for us, like a prototype, and then they want to extend it to Trident eventually, right? Okay. So yeah, what we mean by this 1 sigma, 2 sigma, is that what you're asking? Okay, good. Yeah, so what is plotted here is this what we call the -2 delta LLS. This is the log likelihood. So you can you can think of something like chi-square. Okay, for a Gaussian distribution, you can think of like chi-square. You have a data, and then you have some theory prediction, and you want to compare the theory to your data, right? And data has some error bar. So you can ask the question, okay, within the error bar, how well can I fit the theory prediction with the data? And then you can derive a chi-square, bin by bin chi-square. And then you say that, okay, when is my chi-square more than, okay, for let's say you have 1 degree of freedom, then if your chi-square is more than 2.71, then you say that, okay, I have 2 sigma exclusion of that particular model. And a more fancy way of doing that is by using this likelihood analysis. If you have less number of data points, the Gaussian doesn't really work. So you have to do this likelihood. That's more like what do we call the Poissonian distribution. And you can ask the same question, that when is that likelihood function larger than some number? And if they're larger than some number, then you can exclude that model at that level of confidence. And that's what is basically shown here as 1 sigma and 2 sigma. So the higher the confidence, the higher the sigma, that means you can rule out this scenario at a higher confidence level. And 90% means, well, 99% is like 1 part in 10⁻⁷, something like that. Yeah, so there is some, yeah, you can tell like at what confidence we can rule out that possibility. Yeah, what's the probability of that happening, right? Yeah. Does that answer your question?
Yeah. I have a question that is related to that. Like when we are studying different small intelligence, we are putting a lot of functions.
Right.
We have differently.
Right.
Like model maybe one.
Right.
Every function is given 5%. We are very confused. What to conclude? Is that a problem with the systematic itself, like
Yeah, that's a good question. So we're asking like, why do we have so many models? Why not just one model? All right. Yeah. That's because we don't have a concrete signal yet, right? So once we have a signal, then of course you'll have multiple models, but you can at least tell which model is fitting the data better. Because right now there is only we have constraints, and you can satisfy the constraints in many different models. And so usually theorists are very clever. They can always find a scenario where you can avoid the constraints, and you can have a model to avoid those constraints, right? But so unless we have some signal, some concrete signal, we cannot really tell which model is the best model of the nature, right? Yeah, so that's why we all are waiting for some signals. And until we have that, we can always have this constraint. At least we can rule out models. That's still an improvement. That's still an advancement in the field, right? We can rule out some models, then you come up with either more models, or you just live with whatever remaining models. Yeah.
All right, maybe let's end it here officially and thank Dev again for a very interesting presentation.
Thank you.